So you've made it to the system design interview, the boss level of tech interviews, where your architectural skills are put to the ultimate test. The stakes are sky high. Ace this, and you're on your way to that coveted staff engineer role. Flub it, and it's back to the drawing board. System design interviews have become an integral part of hiring at top tech companies and are notoriously difficult at places like Google, Amazon, Microsoft, Meta, and Netflix. Why? These companies operate some of the most complex systems on the planet, and they need engineers who can design scalable, reliable architectures to keep them competitive. However, you're not alone if this format makes your palms sweat. Most software engineers struggle with system design interviews, finding them a major obstacle in career progression. But fear not, this guide will walk you through everything you need to know to crack the system design interview, even at the staff level. We'll talk about the right mindset, common challenges, and how to tackle them, core concepts explained with simple analogies, sneaky tricks to impress your interviewer, real-world examples from tech giants, and pitfalls to avoid. Understanding the system design mindset. Before you jump into drawing boxes and arrows, step back and change your mindset. A system design interview isn't like coding out a LeetCode solution with one correct answer. It's about high-level thinking, trade-offs, and real-world engineering decisions. In other words, you need to think like an architect, not just a coder. Successful system design is all about balancing competing goals and making informed decisions to handle ambiguity and scale. In fact, system design is about making crucial decisions to balance various trade-offs, determining a system's functionality, performance, and maintainability. Every design choice, SQL versus no SQL, monolith versus microservices, consistency versus availability, etc., has pros and cons, and interviewers want to see that you understand these trade-offs and can reason about them out loud. Equally important is adopting a real-world perspective. Interviewers aren't looking for a textbook answer. They want to know how you build a system that actually works in production. That means considering things like scale, millions of users, reliability, service will fail, then what, and evolution requirements change. Can your design adapt? The best candidates approach the problem like they're already the staff engineer on the job. They clarify what's really needed, weigh options, and choose a design that addresses the requirements with sensible compromises. There's rarely one right answer in system design. What matters is the reasoning behind your answer. One pro tip: always discuss trade-offs. If coding interviews are about getting the solution, system design interviews are about discussing alternative solutions and why you'd pick one over another. In fact, interviewers love it when you explicitly talk about the why behind your design decisions. As one senior engineer put it, hearing candidates discuss trade-offs is a huge green flag that they have working knowledge of designing systems, as opposed to just parroting a tutorial. For example, mention why you might choose a relational database for consistency versus a NoSQL store for scalability, given the problem context, showing you understand the consequences of each choice. Adopting this mindset, thinking in trade-offs, focusing on real-world constraints, and abstracting away from nitty-gritty code is the first step towards system design success. And yes, it's normal for system design questions to feel open-ended or ambiguous. Part of the mindset is embracing ambiguity. Unlike a coding puzzle, a system design prompt might not spell out everything. It's your job to ask questions and reduce the ambiguity. This is exactly what happens in real projects. Requirements are fuzzy, and great engineers ask the right questions. So don't be afraid to say, "Let me clarify the requirements first." That's not a weakness. That's you demonstrating the system design mindset. Common problems and how to solve them. When designing any large system, you'll encounter a few recurring big challenges. Interviewers love to probe how you handle these. Let's break down the usual suspects and strategies to tackle them like a pro. Scalability. Can your design handle 10 or 100 scale more users or data. Scalability comes in two flavors: vertical scaling, running on bigger machines, and horizontal scaling, adding more machines. Vertical scaling, scaling up, is straightforward. Throw more CPU, RAM at the server, but it has limits and can get expensive. Horizontal scaling, scaling out, means distributing load across multiple servers. This approach is more elastic. You can in theory keep adding servers forever, but introduces complexity. You need to split data or traffic and deal with distributed systems issues. How to solve it? Design stateless services so you can run many clones behind a load balancer. Consider database sharding, more on that later, for huge datasets, and use caching to reduce load on databases. Also, identify bottlenecks. If your database is the choke point, maybe you need to replicate it or use a different data store. Scalability is often about partitioning work. More servers, more database shards, more message queue consumers, etc., each handling a slice of the load. Consistency versus availability. In a distributed system, you often have to choose between making data consistent or keeping the system available during network failures. This is the famous CAP theorem. According to CAP, a distributed system can only guarantee 2 out of 3: consistency, availability, partition tolerance. Partition tolerance handling network splits is usually non-negotiable. Networks will have issues, so your system must tolerate it, which forces a trade-off between consistency and availability. Consistency means every read gets the latest write, no stale data. Availability means the system continues to operate serve requests even if some nodes are down or unreachable. You can't have it all, so what do you choose? It depends on the product. For example, in a banking system, you must have strong consistency. Your account balance should not wildly differ between servers, even if that means some waits or downtime. In contrast, for a social media feed or video streaming, availability is king. The system should keep serving content, even if some data might be slightly stale. How to solve it? Decide where you need strong consistency and use databases or techniques that ensure it, versus where you can allow eventual consistency for the sake of uptime. Many modern systems use a mix, e.g., eventual consistency for non-critical data, meaning data updates propagate gradually, but the system never goes completely down. We'll explain eventual consistency with a fun analogy in the next section. Latency. Users hate waiting. Latency is the delay from when a user makes a request to when they get a response. At scale, latency can creep up due to network hops, database lookups, etc. If your design doesn't account for latency, the user experience could suffer. Nobody likes staring at a spinner or loading screen. How to solve it? The mantra is move data closer to the user. Caching is your best friend. Store frequently accessed data in memory. RAM is way faster than disk or network, so that repeat requests are blazingly fast. For example, cache popular web pages or API responses in a service like Redis or Memcached, so you don't hit the database each time. Similarly, use a content delivery network, CDN, to cache static content, images, videos, scripts on servers around the world, closer to users, to reduce round-trip time. If you need to fetch data from a distant server or complex computation, see if you can do it asynchronously or in parallel to hide the latency. Designing with asynchrony, e.g., queuing tasks, can also keep front-end latency low by doing heavy work in the background. In short, identify the latency-sensitive parts of the system serving the main user request path and throw in caches or faster pipelines there. Reserve the slower, batch processing work for offline or less frequent tasks. The result? Your system feels snappy even under load. Fault tolerance. Stuff breaks, machines crash, networks go down, bugs happen. A robust system design needs to expect failures and gracefully handle them. Fault tolerance is about designing the system such that a failure in one component doesn't bring the whole house down. How to solve it? Build in redundancy at every critical point. If one server dies, there should be another to take over. Think multiple app servers behind a load balancer, multiple database replicas with failover. Avoid single points of failure that one database instance or one cache node should not be the sole keeper of your data. Use replication for databases with leader-follower setups, so that if the primary goes offline, a secondary can become the primary. In distributed systems, timeouts and retries are essential. Don't wait forever on a failed service, and try again or route to a backup. Also consider graceful degradation. If a feature or component is down, the system should still serve something, maybe with limited functionality instead of total failure. For instance, if the recommendation service in a video app fails, you can still stream videos just without personalized recs. Bonus points if you mention techniques like circuit breakers, which prevent repeatedly calling a failing service and overloading it, popularized by Netflix's Chaos Monkey experiments. At staff engineer level, you should show awareness that at scale, anything can fail, and your design accounts for it via redundancy, failovers, and resilience mechanisms. Each of these problems, scalability, consistency versus availability, latency, fault tolerance, is a classic area of questioning. By discussing these and offering concrete solutions, add caching, add replication, split the service, etc., you demonstrate a holistic system design thought process. Remember, there's no free lunch. Often improving one area, say, making data strongly consistent, might hurt another, maybe higher latency or less availability. That's why trade-offs are the name of the game. If you can recognize and navigate these common challenges with sensible trade-offs, you're well on your way to cracking the interview. Key concepts and how to apply them. Interviewers expect you to know and understand the building blocks of large-scale systems. But don't worry, these concepts aren't rocket science. Let's break down the key system design concepts in plain English with analogies to make them stick. Load balancing. Imagine a popular ice cream shop on a hot day. One cashier would have a huge line, so the shop uses multiple cashiers and a person at the front directing each new customer to the next available cashier. That's essentially load balancing. In tech terms, a load balancer is a service or device that sits in front of a group of servers and distributes incoming requests so that no one server gets overwhelmed. This is crucial for scaling out horizontally. Common algorithms include round-robin send each new request to the next server in line, or more advanced ones that account for server load. By spreading traffic, load balancers ensure high throughput and help your system handle more users. In an interview, if your design involves multiple servers, e.g. multiple web servers, you should mention a load balancer. Also mention the type hardware load balancers like F5 appliances versus software like HA proxy, Nginx, or cloud load balancing services. Applying load balancing is straightforward. All user requests go to a single endpoint, the load balancer, which then proxies or forwards the request to one of the many servers behind it. If one server dies, the load balancer directs traffic to the others. Voila, basic fault tolerance as well. In short, load balancing is about evenly distributing work to improve reliability and capacity. Caching. Ever notice how the second time you load an app or website, it's often faster? That's caching in action. A cache is like a short-term memory for your system, a fast storage, usually in memory, that keeps copies of frequently accessed data for quick retrieval. Analogy. Think of searching for a word in a dictionary. If you had to get up and walk to the library for each lookup, like hitting a database on disk every time, it'd be slow. Instead, you keep a dictionary on your desk, a cache for the words you look up often. In system design, caching can happen at multiple levels. Your browser caches static files, a CDN caches content near users, your backend might cache results of expensive DB queries in memory. The payoff is reduced latency and load. Caches make reads blazing fast. Memory access can be orders of magnitude quicker than disk or network. When explaining caching, mention cache invalidation, i.e., what happens when data changes. How to keep the cache updated or expire old entries, a classic interview follow-up. Also, differentiate between client-side caching, e.g., browser, app caching data locally, and server-side caching, e.g., a Redis cache layer between your app and database. A good strategy is to cache read-heavy content that doesn't change too often. For example, Twitter might cache a user's home timeline tweets so it doesn't recompute it every time the user opens the app. Just remember the trade-off. Caches can serve stale data if not updated, so decide what can tolerate a bit of staleness. Apply caching wherever you identify a bottleneck in read performance. It's one of the simplest ways to speed things up. Database sharding. This term sounds fancy, but it just means splitting a database into pieces, shards, to spread the load. Suppose you have millions of users and your user data no longer fits on one database server, or one machine can't handle all the queries. You can shard the user table by, say, user ID range or alphabet. Users AM on shard 1, NZ on shard 2, now two databases share the load. An analogy. A library splits its catalog into multiple sections, AL, MZ, rather than one giant list, so librarians can help more patrons in parallel. Sharding is a form of horizontal partitioning of data. Each shard handles a subset of the data and queries, which means each one has less data to manage and can work faster. The system as a whole can handle more because you can add more shards as needed, like adding more library sections. The tricky part is routing queries to the correct shard. Your application or a proxy must know which shard has the data you need, e.g., a lookup service or a hashing scheme on a key. Also, sharding introduces complexity for joins and transactions that span shards, since data is in different places. But it's a powerful tool for scaling databases horizontally. Apply sharding when you have a huge dataset or write-heavy workload that one machine can't handle. For instance, Instagram might shard user data by IID, so that queries for different users hit different database servers, preventing any one DB from being a hotspot. Mentioning a sensible sharding strategy in an interview, like "we can shard by user region" or the first letter of username, shows you're thinking about growth and scale. Eventual consistency. Earlier we talked about consistency versus availability. Eventual consistency is a model where you allow some inconsistency in the short term, with the guarantee that if you wait a bit, the system will become consistent. It's like gossip among friends. Not everyone hears the news at the exact same moment, but eventually everyone will know the latest info. Since, here's a fun analogy. Strong consistency is like a formal dinner. It doesn't end until everyone at the table has been served the exact same meal. In contrast, eventual consistency is like a buffet. People finish eating at different times, and that's fine, because eventually everyone will get food. In tech terms, eventual consistency means when a user updates some data, say, posts a new photo, not all servers or replicas see that update immediately. One server might still show the old data for a short while, but if the system is working correctly, all the replicas will eventually synchronize the update. This is common in distributed databases, e.g., NoSQL stores like Cassandra or Dynamo-style systems, where the emphasis is on high availability and partition tolerance. The upside: the system remains available, no waiting for all replicas, and it can be blazing fast because you often read from a nearby replica without worrying if it has the absolute latest byte. The downside: you can read slightly stale data. How to apply it? If your system can tolerate slight delays in propagation, e.g., a social media feed or analytics data, eventual consistency is a great choice. You'd use databases or caches that replicate updates asynchronously. Just be ready to explain to the interviewer which parts of your system need to be strongly consistent, e.g., a user's password change or money transfer versus which can be eventually consistent, e.g., profile view counts, feed updates. Many real-world systems mix both models. Critical data is strongly consistent. Everything else is eventually consistent for better performance. CAP theorem: consistency, availability, partition tolerance. This is a theoretical concept that often underpins the consistency versus availability discussion. The CAP theorem states that in the face of a network partition, nodes unable to communicate, a distributed system must choose either consistency or availability. In simpler terms, you can't guarantee 100% consistency and 100% uptime in a distributed scenario. You have to make a trade-off. We've touched on this already, so here's how to apply it. First, recognize if the system you're designing is distributed, multiple nodes in different network partitions. If yes, tell the interviewer which side you'd lean on in a partition. Do you choose to remain available, serve possibly stale data, or to be consistent, perhaps refusing requests until the partition is resolved? That decision should be based on the use case. Many web services choose availability because an inconsistent minor piece of data is better than an outage. Think about reading tweets. You'd rather see slightly old tweets than an error message. Conversely, some systems' banking ledgers choose consistency, even if it means an operation might not be available until things synchronize. Mentioning CAP theorem explicitly can earn you bonus points, but more important is showing you grasp the implication. You will design your system to favor either C or A when P happens. For example, you might say, in our chat app design, if a network partition occurs, I'd prioritize availability. The chat service will still accept messages and deliver whatever data it has, and resolve consistency once the network is back in AP approach. This demonstrates a high-level command of distributed systems thinking. Those are some heavy-hitter concepts. We could add more like rate limiting, preventing overload by capping requests, or CQRS, separating read-write models, etc., but the ones above are usually sufficient to show mastery. The key is not just name-dropping these terms, but applying them appropriately in your design. Use analogies if it helps interviewers appreciate clear communication. If you can explain, say, caching or sharding in simple terms and then weave it into your solution, will shard the database by user ID to handle the scale of 10 million users, you'll stand out as someone who's both technically solid and practically minded. If you made it this far, consider liking and subscribing. It's free and helps reaching a bigger audience. Tricks to crack the system design interview. Alright, now let's talk strategy. Knowing system design concepts is one thing. Delivering a great interview answer is another. Here are some tried and true tricks to help you structure your response and impress your interviewer. Start by clarifying requirements. The biggest mistake is to rush into drawing architecture without knowing what you are solving. So, ask questions and nail down the scope. What exactly should the system do? What are the use cases? How many users or requests are we talking about? This helps gauge scale. Are there specific constraints, e.g., security requirements, latency needs, data consistency expectations? This isn't wasted time, it's critical. Interviewers actually expect you to do this. For example, if asked to design a URL shortener, clarify. Do we need analytics? How long should links live? Expected read-write ratio. By clarifying, you show a structured approach and avoid solving the wrong problem. Lack of clarity in requirements is cited as a top reason candidates fail system design rounds, so don't fall in that trap. Spend the first 5-10 minutes defining the problem with the interviewer. It's totally okay to do so. Outline a high-level design. Once you're clear on requirements, sketch a high-level architecture before diving into details. This is like drawing the map before zooming into each city. Identify the major components your system will need. For instance, say you're designing Twitter. You might outline clients, mobile app, web, a load balancer, service layer, tweet service, user service, databases for users and tweets, a caching layer, etc. Keep it reasonably abstract at first, maybe just boxes like web servers and database, the broad strokes. This high-level picture shows you have a plan and covers the system end to end. It also gives the interviewer a chance to say, okay, let's focus on this part or that part, guiding you to where they want to drill deeper. By getting buy-in on the high-level design, you ensure you and the interviewer are on the same page. One trick: mention that you're open to refining it. For example, here's the overall design I'm thinking. Users, dry load balancer, poller-in, app servers, piler-in, plus a cache and a queue for background processing. Does that sound reasonable, or should I consider something else? This invites feedback and makes it a conversation. Break it down into components. Now take each major component and discuss how to design it or address any challenges with it. Focus on the core challenges, bottlenecks first. A good structure is to go through the main user flow, e.g., user makes a request to shorten a URL, hits the web server, server writes to database, returns the short URL. Later, a user clicks a short URL, hits our system, we look it up in db.cache, redirect to the original URL. By walking through the flow, you ensure you cover all moving parts. For each part, mention relevant concepts. We'll use a relational DB to store the mappings because we need transactions to avoid duplicate shortcodes, and we'll add an in-memory cache to speed up reads for popular URLs. Also address trade-offs and alternatives as you go. We could use NoSQL here for flexibility, but consistency on the shortcode mapping is important, so SQL is safer. This structured breakdown shows depth. It's often useful to organize by subtopics like data storage, application logic, scaling the system, and any special feature, e.g., how do we handle analytics. Address each systematically. Manage time and depth. Use the interviewer's cues. In a 45 to 60-minute interview, you won't be able to cover everything in extreme detail. A smart candidate prioritizes and also listens to the interviewer for hints on where to dive deeper. If they ask a pointed question, e.g., how would you handle failover in the database, that's a clue they want you to explore fault tolerance on the storage layer. Follow that lead. On the flip side, if you have a lot to discuss, you can ask, is there a particular area you'd like me to focus on, such as scaling the database or the messaging between services? This ensures you spend time where it matters. Be adaptive. If mid-discussion the interviewer says, actually, how would the design change if we need real-time updates? Roll with it. That's a common tactic. They change or add a requirement to see how you pivot. Don't get flustered. Acknowledge the new requirement and think out loud about adjustments. For example, okay, real-time updates mean our current design might need a push notification service or WebSockets. Let's see how we can integrate that. Showing you can handle the unexpected gracefully is huge. In fact, being flexible is part of demonstrating senior-level skill, because in real life, requirements and constraints change all the time. Address bottlenecks and trade-offs. Proactively. After presenting the main design, take a step back and identify potential weak points in your architecture. This could be a single database that might become a bottleneck, or a dependency that if fails could crash the system. Point these out unprompted, e.g., one concern is that our single cache server is a single point of failure. We should use a cluster for our cache, or have a backup strategy. Or, As traffic grows, the database will have to be sharded or use read replicas to handle load, which adds complexity. By doing this, you show ownership of your design and a forward-thinking approach. Also discuss any trade-offs you made. We chose an AP highly available design for the feed service, meaning users might see slightly stale data, which is a trade-off we accept for lower latency and better uptime. Mentioning such trade-offs and why you chose one over the other reinforces that you understand there's no one perfect system and you're making conscious, rational decisions. Communicate clearly and involve the interviewer. A system design interview is as much about communication as it is about architecture. Explain your thought process out loud. Use the whiteboard or shared doc to draw as you explain, and keep your structure logical. Don't just monologue for 30 minutes. Periodically check in. Does that make sense, or anything you'd like me to delve into more? Treat it as a collaborative discussion. Often, interviewers will play along and ask questions or pose scenarios. What if we suddenly had 10x more users in a certain region? This is a good sign. It means they're engaged. Answer their questions methodically, and if you don't know something offhand, it's okay to say you'd make an assumption or use a reasonable default, e.g., I'd use a standard consistent hashing technique to distribute keys across cache nodes. The specifics can be ironed out. It's better to thoughtfully reason through a challenge than to awkwardly guess an answer. And remember to be confident but not arrogant. If the interviewer corrects something or offers an alternative, acknowledge it and build on it. They want to see that you can work through a design problem collaboratively, not just that you memorized one. By following these steps, clarify high-level design, drill down into components, handle surprises, address trade-offs, communicate, you create a narrative for your solution. It shows you're organized, thorough, and thinking on multiple levels, requirements, scale, trade-offs, etc. It's essentially demonstrating how you'd approach designing a system in real life. One more trick: use simple language and occasional analogies even in this discussion. If you can explain a complex idea like eventual consistency or sharding in an easy way as part of your answer, it not only shows mastery, but also communication skills, a must at staff level. For instance, we might shard the database, basically split the data into chunks, maybe by user region, so that users in Europe are on a different shard than users in America, which reduces the load on each database. This could help the interviewer follow your design choices and see that you can explain things to teammates, a key skill for a senior engineer. Finally, keep an eye on the time. If you find yourself deep in one rabbit hole, like, say, tuning a caching strategy, and only 5 minutes remain, make sure you at least outline other areas you didn't get to. We haven't talked about security or monitoring, but I'd also ensure we log events and have metrics, and secure user data with encryption. This shows completeness, even if briefly, and can save you if time management got away a bit. But ideally, you pace yourself to cover the main points with a few minutes to spare for any follow-up questions or a quick summary.
Real-world examples. To really understand system design, it helps to see how real companies do it. Let's look at a few real-world examples that also double as great talking points in interviews. Netflix. Netflix is a poster child for massive scale. They serve streaming video to hundreds of millions of users around the globe, which means insane amounts of data and a need for ultra-high availability. How do they do it? One key is that Netflix uses a global content distribution network called Open Connect, basically their own CDN that caches Netflix content on servers close to users' ISPs for faster delivery. This ensures that when you hit play, the video stream comes from a nearby server, maybe even at your local ISP, rather than halfway around the world,
drastically reducing latency and buffering. Netflix also heavily embraces microservices. Their system is split into countless small services for user profiles, recommendations, search, etc., each scalable on its own. And they've invested in fault tolerance perhaps more than anyone. They famously created Chaos Monkey, a tool that randomly kills servers in production to ensure Netflix's systems are resilient to failures. The result is an architecture where no single failure takes down the whole service. If you're asked something like design a video streaming service mentioning Netflix's approach, like using a CDN for content, stateless streaming servers, and maybe a microservice for each function, authentication, catalog, streaming, user data, is a great way to justify your design. It shows you're aware of how the pros do it. Netflix is also known for choosing availability over consistency in many cases. For example, they would rather let you keep watching shows even if some personalization data is momentarily inconsistent than interrupt your binge. Everything about Netflix's design screams scale. They handle billions of hours of content viewing per month by deploying on AWS and their CDN with tons of automation. It's a perfect example of combining caching, load balancing, and partitioning to achieve global performance. Uber. Uber's system needs to handle real-time updates for rides, match drivers and riders, and stay reliable across cities worldwide. In Uber's early days, they hit some painful scaling issues. For instance, concurrency bugs where two drivers would get assigned to the same rider or vice versa. Those issues were due to the challenges of coordinating a lot of data drivers, riders, locations on a monolithic system. Uber addressed this by overhauling their architecture for scale. They moved from a monolithic setup to a microservices architecture split by domain trips, payments, user management, etc., which allowed teams to scale each part independently and deploy faster. For example, the dispatch system matching drivers to riders became its own highly optimized service. Uber also heavily uses in-memory stores for live tracking. Imagine needing to update and read driver locations extremely quickly. A distributed in-memory system can handle those reads, writes far faster than a disk-based DB. They introduced an extra layer called the gateway or API service that all clients talk to, which then calls the relevant microservices behind the scenes. This gateway helps with versioning and backward compatibility as the mobile apps evolve. And for data storage, Uber uses a mixed relational databases for some things, NoSQL for others, and big data pipelines for analytics. One interesting thing about Uber, it's both real-time and geo-distributed. They had to ensure that when you open the app, you see drivers near you with minimal latency. To achieve this, Uber did things like splitting data centers by region and even optimizing networking between them. They also chose availability in many cases. For example, if one small part of the system, like the system calculating ETA estimates, fails, that shouldn't stop you from booking a ride. You might just not see an ETA, but you can still get a car. Uber's journey has many lessons. Fixed bottlenecks. They rewrote critical parts in more efficient languages like Go, break the system into smaller pieces, microservices, and always prepare for the next 10x growth. If an interviewer asks about designing a ride-sharing service, referencing Uber's approach, e.g., we'd likely need to separate the real-time dispatch component from other parts, similar to how Uber did, to handle live updates independently, will show you've done your homework on scalable architectures. Twitter. Twitter might seem simpler text messages, what's the big deal? But under the hood, it's a classic example of tackling read-heavy workloads and eventual consistency. Twitter's primary challenge is the fan-out of tweets. If I have 100 followers and I tweet, that's 100 timelines that need updating. If a celebrity with 10 million followers tweets, you get the idea, it's huge. Early on, Twitter discovered a single chronological timeline approach couldn't keep up, so they implemented strategies like pre-computing and caching timelines. In fact, Twitter will often push new tweets to the home timeline caches of followers, especially for users with many followers, so that when you open the app, it just reads from a cache, not recompute from scratch. They use systems like Redis as caches for timelines. This is a great example of eventual consistency in practice. When a tweet is posted, not everyone might see it instantly, but within seconds it propagates through the system. And if a cache hasn't updated yet, a user might see an older timeline until it does. Twitter decided that's fine, again, availability over strict consistency for the feed. Twitter also deals with huge volumes of read traffic, billions of timeline views, which they handle through heavy caching, load balancing across many servers, and dividing responsibilities, the user service, tweet service, social graph service, for follow relationships, etc. Another interesting point: search on Twitter finding tweets by keyword is powered by a separate system, an Elasticsearch cluster, historically because that's more of a text search problem distinct from the real-time timeline problem. By separating those concerns, Twitter can scale each part appropriately. And like others, Twitter's architecture has evolved. They've broken the monolith, introduced queues, Kafka for reliable delivery of tweets to various consumers like the timeline generator, search indexer, analytics. If you're asked about designing a social network feed, you can mention Twitter's trade-offs. We might not update every follower's feed in real time, but instead use an eventual consistency model where feeds are updated asynchronously and cached. This is how Twitter handles a single tweet fanout to millions of users without melting down. Real examples like that can solidify your argument for using a certain approach. Bringing up real-world architectures not only shows that you've studied them, but also grounds your design choices in reality. It's one thing to say I'll use a CDN and caching, it's stronger to add, just like Netflix does, to deliver videos with low latency. It signals that your ideas have precedent in successful systems. That said, be ready for the follow-up. If you name drop a tech used by these companies, Kafka, Cassandra, etc., make sure you can briefly explain why it's used. E.g., Kafka, a durable message queue, is used by Twitter to buffer writes and decouple components for the feed, ensuring reliability and async processing. But even a high-level reference, as we did above, can make your solution more convincing. It shows you're aware of how scale is handled in the wild.
Common mistakes and pitfalls. Nobody's perfect, and in system design interviews, there are some common pitfalls that can trip you up. Here are the top mistakes candidates make. Don't be that candidate and how to avoid them. Jumping into design without clarifying requirements. We've emphasized this, but it's worth repeating. Failing to understand the problem is the quickest way to design the wrong system. Many candidates just start drawing an architecture for the thing they think the interviewer means and go off track. Avoid this by asking questions up front. If the prompt is, design Facebook Messenger, clarify things like, are we doing just one-on-one chat or group chat as well? Do we need message history, voice calls? What's our target scale, millions of users? This ensures you solve the right problem. Interviewers have noted that lack of clarity in requirements is a significant reason for failure, so take a moment to gather requirements and confirm assumptions. It's much better to spend a few minutes up front than to realize 30 minutes in that you designed something that doesn't meet a key requirement. Overcomplicating the design. Another pitfall is feeling like you have to throw in every buzzword and design pattern you've ever heard of. Candidates sometimes draw 15 microservices, 6 databases, 4 different caches,
when the problem could be solved with a simpler approach, at least at first pass. Remember, you can always add complexity if needed, but if you start too complex, your design might become incoherent. As one expert notes, you should draw the necessary components, but don't overdo it. Overcomplicating the design can confuse both you and the interviewer and obscure your thought process. Avoid this by starting with a basic design, then iteratively enhancing it. It's fine to say, initially I'll start with a simple architecture, one service and one database. Now, given the scale, we'll need to add XYZ. This way the interviewer sees the progression. Over-engineering in an interview can also signal that you're not good at prioritizing, or you're just regurgitating memorized designs without tailoring to the question. So keep it as simple as possible while meeting the requirements. A clean, comprehensible design with a few well-justified components trumps an excessively complex one any day. Premature optimization. This is a classic mistake in both coding and system design. In an interview, this might look like diving into performance tweaks or minor details too early, e.g., talking about how you'll use a special indexing strategy on your database before you've even decided which database or what your data model looks like, or obsessing over how to save a few milliseconds on an API call while ignoring bigger architecture decisions. Don't optimize too early. Optimize after you have a working design outline and when you've identified actual bottlenecks or hotspots. For instance, don't start the design by saying, we'll need caching and sharding from the get-go for a relatively straightforward problem, unless the scale absolutely demands it. Focus on the big picture first. If and when you identify a scalability pain point, then suggest an optimization. Remember that every optimization, like introducing a cache or additional partitioning, also adds complexity. As one guide warns, it's a red flag to get carried away with premature optimizations. Adding things like caching.sharding too early can distract from the core design and are often not justified initially. In other words, build first for clarity and correctness, then optimize for scale-out performance as a second step. You can literally say, first I'll design a correct system, then we'll talk about scaling it up. This way the interviewer knows you're not just ignoring scale, you're sequencing your approach. By avoiding premature optimization, you also avoid premature complexity, tying to the overcomplication point above. Not addressing trade-offs or alternative choices. Some candidates present their design as if it's perfect and never acknowledge that other approaches exist. This can make it seem like you're unaware of the downsides of your decisions. For example, if you choose ASQL, the trade-off might be scaling is harder versus a NoSQL solution. If you choose eventual consistency, the trade-off is stale reads versus the benefit of uptime. Make sure at some point you mention the key trade-offs in your design. If you don't, an interviewer might explicitly ask, what are the drawbacks of your approach? You should be ready. A common mistake is to get so wrapped up in your one design path that you forget there were other ways. To avoid this, occasionally say things like, we could also have used X here, but I chose Y because, or the downside of this design is Z, but we mitigate that by. This shows maturity. Neglecting to discuss trade-offs can make your design seem one-dimensional. So even though it's an interview mistake, think of it as an opportunity. By proactively discussing trade-offs, you stand out as someone who thinks critically. Forgetting non-functional aspects, if time permits. While perhaps less common in interviews due to time, at a staff level you are expected to at least mention things like security, monitoring, and maintainability if they are relevant. Candidates often focus only on scalability and performance and forget things like data privacy, API security, auth.auth, or how they'll monitor the system in production. If you have a minute at the end, or if the interviewer hints at it, say a few words on these. For example, we should also secure our APIs, maybe using OAuth for user-facing services, and ensure we have proper logging and metrics for monitoring the health of the system. It doesn't have to be detailed, but it shows you think like an owner. Many a time, failing to consider non-functional requirements can be a pitfall, like designing a great system that isn't secure or is a nightmare to maintain. So try to touch on at least one or two such aspects. Security, reliability, we did that with fault tolerance, maintainability, like keeping the design modular, etc. This rounds out your answer. Poor communication and organization. This isn't a design mistake per se, but it's a killer in interviews. If you have great ideas but communicate them in a very disorganized way, the interviewer might get lost or doubt your leadership skills, which are important at senior levels. Avoid this by structuring your answer, use the tricks from the previous section, and speaking clearly. Common pitfalls here include jumping around the diagram with no structure, mumbling or going silent for long stretches without explaining your thought process, and not engaging the interviewer. The interview is as much about how you think as what you propose. If something isn't clear, don't be afraid to draw it out or use an example. If you realize midway that you made a mistake, it's okay. Note it and correct. I mentioned one database earlier, but given the scale we discussed, that should actually be a cluster of databases, or it won't handle the load. Interviewers appreciate clarity and adaptability more than stubbornly sticking to a flawed approach. To sum up, clarify requirements, keep design simple, then scale up. Don't prematurely optimize, always mention trade-offs, consider the interleave scalability, reliability, security, etc., and communicate clearly. If you avoid the pitfalls above, you'll avoid most common reasons candidates flunk system design interviews. And if you do all the positive opposites of those mistakes, you'll likely knock it out of the park. Final tips and resources. Congratulations, you've made it through the core of system design prep. Before we send you off to conquer that interview, here are some final tips and excellent resources to further sharpen your practice. There's no substitute for actually designing systems. Pair up with a friend or colleague and do mock system design interviews. There are platforms like Pramp and interviewing.io where you can practice with strangers or mentors. Even self-practice helps. Take a few common design problems, design YouTube, design an online multiplayer game system, etc., and sketch out solutions on paper or a whiteboard. The more you practice, the more comfortable you'll get with thinking on your feet. Also consider timed practice. Give yourself 30 to 45 minutes to simulate the pressure of the real thing. This helps with time management, and when practicing, speak aloud or explain to someone. This will improve your communication skills for the real interview. Study real-world architectures. We touched on Netflix, Uber, Twitter, but don't stop there. Read up on how other big systems are designed. Facebook's photo storage system, Amazon's ordering system, Google's big table and spanner papers if you're inclined, etc. Many tech companies have engineering blogs that are gold mines of info. For instance, the Netflix tech blog, Uber engineering blog, Twitter engineering, Facebook engineering. They often post articles about the challenges they faced and solutions they implemented. Studying these will give you insight into why they chose certain designs. You'll start noticing patterns and common practices which you can then apply in interviews. Even case study books or sites like highscalability.com provide summaries of famous architectures. This not only helps you learn new techniques, but also arms you with cool anecdotes to mention. Interestingly, this is similar to how XYZ solves this problem in their system. Tech conference talks on system design, like from AWS reInvent or Google Cloud Next, are also great. Many are on YouTube for free. Leverage great resources. There are some tried and true resources out there specifically for system design interview prep. For example, the Grokking the System Design Interview course, Design Gurus, is popular for covering common interview questions. The System Design Interview, an Insider's Guidebook by Alex Xu, 2 volumes, is a fantastic compilation of problems and solutions. And for deep foundational knowledge, Designing Data-Intensive Applications by Martin Kleppmann is highly recommended. It covers the principles of distributed systems in an extremely readable way and will give you confidence in understanding consistency models, data systems, etc. Many consider it a must-read for system design. You don't have to read everything cover to cover, but going through a structured resource can fill gaps in your knowledge. Additionally, websites like Educative, Exponent, and ByteByteGo offer courses or newsletters on system design. For instance, ByteByteGo by Alex Xu regularly shares system design tips and examples. Use these to broaden your understanding. Online communities like the ar.systemdesign subreddit or Stack Exchange can also be helpful if you have specific questions or want to see how others approach problems. In summary, take advantage of the wealth of material, online courses, books like Grokking or Alex Xu's or Kleppmann's, and tech blogs white papers from real companies. All are excellent resources to learn system design. Think in terms of trade-offs and justified choices. As a final mental checklist, remember that there's no single perfect design, so when preparing, practice the art of making a choice and justifying it. Always ask yourself, why did I choose this approach? What are its pros and cons? What would I do if requirements change? This mindset will help you dynamically adapt in an interview. It's okay if your initial design isn't bulletproof, none are. What matters is that you can discuss how to improve it or what the considerations are. Showing that you can evaluate different options and pick one based on reasoning is key for a staff-level demonstration. During the interview, stay calm and have fun. Yes, system design interviews can be intense, but they can also be surprisingly enjoyable. It's like jamming with a colleague on a tough problem. Approach it with a problem-solving attitude rather than a test to be feared. If you've prepared and practiced, trust yourself. If you get stuck, you can always take a short pause, think, or even say, let me take a moment to consider how to tackle that. It's better to gather your thoughts than to panic. Interviewers appreciate a structured thinker, not necessarily someone who blurts out instant answers. And don't forget to smile if appropriate and show some enthusiasm. After all, a system design interview is a chance for you to showcase that you love designing systems. If you appear genuinely engaged and interested in the problem, that positive energy can go a long way. Lastly, remember that every system design interview is also a learning experience. Win or lose, you'll gain something to carry into the next one. Keep refining your approach, collect feedback, and you'll continuously improve. By studying real systems and practicing regularly, you'll build an intuitive sense for architecture that no one can stump you on easily. Good luck! You're now armed with the ultimate guide, technical knowledge, strategies, examples, and resources to crack that system design interview. Go forth and design some great systems, and maybe even enjoy the process on your way to becoming a staff engineer. That's it for today's episode. See you in the next one.